Hi everyone, I'm John. I'm a crop scientist and a SAS employee. Today, it's my pleasure to introduce you to mixed modeling, show you what it is and how to do it. And for those of you who are already skilled in mixed modeling, I'd also like to show you how to scale mixed models using the power of SAS Viya. Now, before I go any farther in this demo, I'd like to qualify that the things I'm going to talk about and the way I'm going to characterize different terms are specific to my field as an agricultural scientist. Different fields use mixed models in different ways and have different sets of assumptions that go along with the paradigms for those fields. So take this as an example of how to use the tool for a particular set of assumptions. People in different fields may hold different assumptions and may use mixed models differently as well. But one thing's for sure, SAS for mixed models is incredibly popular. It's been cited over 400,000 times in the literature, and so it's certainly a tool worth knowing no matter what field you're in. Now I'm going to show you how it's done. First, we're going to parameterize a model and then look at the fixed effect only context. First, we're going to import the data. Data imported. Excellent. Now what we're going to do is we're going to open up the SAS tasks. Go to the glyph on the left-hand side and open up tasks. SAS tasks. And you're going to find mixed models under statistics right there. So for our edification and experience today, we'll be looking at a sample data set of a natural ecosystem called a heath environment. Heath is a type of plant growing in a natural environment somewhere in Europe. And what was done to this heath environment is that there were 4 different treatments applied within the environment. There was a drought treatment, a nitrogen treatment, and a drought and nitrogen treatment, as well as an untreated control. And by the way, there were 2 environments where the same design was applied. Now, many people who run ANOVAs or mixed models, which is an extension of an ANOVA, would treat this as a one-level model, i.e. you treat the treatment as a factor and you have 4 levels, and you derive a statistic and a p-value associated with that one factor. The p-value would tell you whether any of these 4 levels are different from one another. For example, whether control was different from the other 3, but it wouldn't tell you necessarily which ones were different until you ran a post-hoc analysis. Now, post-hoc analysis, depending on which one, more or less assumes independence among the levels, but we can see here independence is clearly not a valid assumption. Instead, a much better assumption is to say, you know what? The treatments with drought are more related to the treatment than the control treatment, and the treatments with nitrogen are more related to the control as well. Hence, treat this as a multi-level model or a factorial model where you break up the one treatment column into 2 columns, one with drought, one with nitrogen fertilizer, and test each of these levels, drought and nitrogen, and the interaction between them. That fully uses the power of this experimental design. So how do you do that? Go to SAS tasks, prepare data, transform data, recode values. Now the columns are split into 2. Very good. Okay, so now we head on down to mixed models in the statistics section and the linear model section of SAS tasks. Let's open it up. So first we'll pick our response variable. We'll do shoot centimeters 2009. We'll choose our classification variables. Regardless of the character or numeric format, some variables should always be classification variables, like ID variables such as plot ID. Okay. We've chosen our classification variables. Now we'll go on to the model and add our fixed effects. our fixed effects in this interest are units of replication that we're interested in. We're certainly interested in drought, fertilizer, and let's say we're also interested in the site. This test was done at 2 different sites. Let's say we're only interested in the effects of drought and nitrogen at those 2 sites specifically. We can add those as single effects, but because each of these treatments was applied in every case within the treatments, we can consider this a full factorial, meaning that we have each of the individual treatments here, as well as the 2-way interactions between everything, and because there are 3 different factors, there's also a 3-way interaction in here. Most mixed modelers start by including all putative or possible interactions in the model. If certain interactions are not significant or are not of interest, those can be taken out later on. We're also going to go to options and choose some options for our study. So first of all, we're going to ask for additional statistics. That could include the type 3 tests. Okay, so now we've chosen our fixed effects, and for now we're not going to add any random effects. Mixed models are mixed with random and fixed effects, so this is going to be a fully fixed effect model that would be identical to an analysis of variance or in ANOVA. We're going to head and explore the options, and what we see here are different plot options such as residuals or studentized residuals or Pearson residuals. The difference among these is that the residuals do not account for the conditional or random variance, and the others do. So in this case, because it's a purely fixed effect model, our residuals would be identical between these. Residual plots are very important because they help test whether the assumptions that you used for this type of modeling were correct, and ensuring that the assumptions were correct for this type of modeling will help ensure that you get a valid output at the end of the day. For now, let's just go with the residuals. Run. Now we have our output. Let's open this in a browser tab so we can see it more clearly. Okay, so we have the model information, class level information, etc., etc. The first thing that most people look at are the p-values of each of the things. And looking at each of the effects, each of the fixed effect parameters that we input into our model, we see none of them as significant at the p.05 or p.10 level. So that means our model isn't able to tell us very much about this data, right? Another thing to look at is the residual plot. One of the assumptions of ANOVA is that your residuals are independent of the predictions. Hence, in this residual plot, you ought to see a very good scatter among residuals for the mean predictions. And this scatter isn't bad. You also assume normality of residuals around 0, and this distribution is fairly normalized. Another way to look at that is the QQ plot, where you would expect a normal distribution to fall pretty squarely along this diagonal line. It doesn't look too bad in this case. So on the bright side, we found a model that abides by the assumptions for mixed models. But on the downside, there's nothing statistically significant here. And so we may want to reallocate the variance in the study so that we can make conclusions about what we're actually interested in, which are the effects of drought and nitrogen across heathlands. Let's give that a try. So I'm going to go back to the model and go ahead and remove site from the fixed effects. We want to consider the site as a random effect. Now, one commonplace heuristic is that if you consider a certain factor random, then everything that could interact with that factor should be considered random as well. So we're going to go ahead and remove all interactions that include Heathland site. And because we're considering drought and nitrogen fertility and their interaction as fixed effects going forward, we're simply going to remove Heathland site from the fixed effect to the random effect. Let's go ahead and add a random effect. The interface for building random factors is very similar to that for building fixed factors, except you have more levels and more options. You're able to capture hierarchies of random effects using this setup. So for example, each of our field sites has blocks within each field site, and those specific blocks are specific to those individual field sites. There's no relationship between block 1 at field site 1 and block 1 at field site 2. So what we're going to do is we're going to consider block as a model effect and site as a subject effect to capture the hierarchy among those two levels. Finally, we're going to consider intercept random, allowing the intercept to vary with the levels of the factors in addition to the slope. All right, so this looks like it could be a good model. We have drought, nitrogen, and their interaction, and block within Heathland site as random effects. So our hypothesis is that there's no difference among the different factors in this multi-level study, and we want to extrapolate those effects across all environments represented by the environments that were studied. Let's go ahead and run this model. Okay, we see a very similar output before, except now we have covariance parameters. Those are our random parameters. We have covariance parameter estimates for the intercept, the block, and the site, and the residual is the total unexplained variation. And then finally, we have our type 3 test of fixed effects with our p-values and our conditional residuals. Looking at the conditional residuals, I wouldn't say we see a perfect scatter or a perfectly normal distribution, but I've certainly seen worse models, and I would call this a not too extreme deviation from the assumptions of normality and independence of the residuals. Now, there are ways we can modify the covariance matrix to perhaps derive a better scatter and better model the residuals given our assumptions. But for now, we'll go ahead and move on to the p-values and do some interpretation. So what we see are p-values much higher than 0.05, much higher than 0.1 for drought and nitrogen, but we do see a significant interaction between drought and nitrogen, which suggests that as drought is applied, the response to nitrogen changes, or vice versa. So in that case, you may want to slice the different effects so that you can discern the effect of drought at each level of nitrogen, or nitrogen at each level of drought. Cool, that's not too bad. But I feel like this isn't telling us the whole story. In fact, this study was replicated over 3 years at the same sites with the same design. Well, those repeated measures provide additional information for us to increase the power of the experiment and additional covariances for us to account for. So how do we account for these 3 years in which the effect of drought and nitrogen was tested at each of these two sites and their effect on shoot weight? Well, what we have is a wide file. That is a file where we have 3 response variables in separate columns from each other. What we need to do is we need to transpose this into a long file where we have each of the years listed in one column. What we will do is we will use the transpose SAS task to turn our wide file into a long file. Let's do it. Transposition done. We now have the year running down the column and one response variable, and now we're able to take that into our mixed modeling program and model the covariance of not only the blocks within the sites, but also all of that within the different years. Let's give that a try. We've changed out our data to the long file. Now we'll go ahead and select the dependent variable, which is shoots centimeter. And we'll now add year among the different classification variables. Our fixed effects will be identical to before. As will our random effects. And finally, we're going to add a repeated effect, the year being the repetition. We'll go ahead and select some new options this time. So let's select studentized residuals. Let's say we want to show some additional statistics. Okay, so now we've derived a model where we're modeling shoot centimeter for drought, nitrogen, and the interaction between the two. We're considering site as a random effect, and blocks are within sites. And then finally, we have everything modeled within groups of years. Let's go ahead and check our residual plot to see if it abides by our assumptions. Not too bad. A good scatter around the predictors, not unlike a normal distribution of residuals around the mean, and a pretty good stratification along the line in the QQ plot. I would say this model abides by our assumptions. There's no serious departures. Let's take a look at our type 3 tests of fixed effects. So we see that drought does not have a significant p-value associated with it. Nitrogen fertility certainly does, well less than 0.05. And drought by nitrogen fertility, 0.776, is above a p-value of 0.05, but below 0.1. Whether that's statistically significant depends on your purpose, depends on the status of your field. Certainly, statistical significance and a threshold p-value shouldn't be the sole basis of a scientific or a business decision. In fact, that's where these estimates really come in handy, right? Let's take a look at nitrogen fertility. It has an estimate of 0.5815. That means for the treatments with nitrogen added, there is an increase of shoot length of 0.58 centimeters within this confidence interval, okay? The interaction shows us that adding drought to that actually decreases the effect of increased shoot length on nitrogen. That's the nature of the interaction. When another level is added, something of that original level changes. So drought more or less washes out the effect of nitrogen fertilization. Pretty cool, huh? It may not be statistically significant at the 0.05 level, but certainly that's something to pay attention to in looking at the effects of perturbations on this ecosystem. Another thing to keep in mind about statistical significance is that p-values and confidence intervals are two sides of the same coin. And so if you have a little bit more rigidity in what you would accept to falsify a null hypothesis, you'd want to increase your confidence interval. However, if a p-value of 0.1 is acceptable to you, then you can decrease your confidence interval commensurately to 90% or whatever is chosen. I hope you enjoyed the demo of the SAS Mixed Model task. I hope it provides a basis for you to continue mixed modeling. One other thing to mention is that within details, you can also choose the denominator degrees of freedom method. Statisticians worry about the degrees of freedom method because so much of the statistic depends on the degrees of freedom. Suffice to say that for small samples such as that which we worked with here today, the Kenwood-Roger 2 degree of freedom is often the preferable degrees of freedom method. But check out other degrees of freedom method and find the one that works best with your data set. All right, now for those of you who are seasoned mixed modelers, working with bigger and bigger data sets, making bigger and bigger conclusions, now I'm going to show you how to take your mixed model practice to a whole other level with SAS Viya. With this, we can run our mixed model computations in memory in a multi-threaded environment. That means minutes, not hours, for a complicated computation of mixed models. Secondly, we can create a partition in our data set with a holdout sample for which we can take our fit mixed model from the training sample and judge the accuracy based on the residuals left in the holdout sample, and thus do our modeling work on par with machine learning models. In fact, we can do them in the same pipeline and compare the effectiveness of our mixed models with that of machine learning procedures such as gradient boost or random forests. So the first thing we'll do is use a partition to assign a holdout sample to our data. All right, so now we've assigned a partition. Let's open up Model Studio and get going with scaling our mixed models using SAS. So now we're in Model Studio where we're going to run the same test in a pipeline where we have the test itself, a predictor node, and then a model comparison node should we have multiple models. In our SAS code node, we open it up and we see code that's very similar to what we ran in our SAS task. However, instead of proc mixed, we're now running proc L mixed, and with a couple of other minor changes to the code, including macro variables, we're now able to run this model in memory using the power of multi-threaded processing. Additionally, there are other nodes, such as supervised machine learning nodes, that we can run alongside our mixed model. And let's go ahead and put in a gradient boosting node to run our mixed model alongside a gradient boost so that when we come to model comparison, we can compare the accuracy of the predictions of the mixed model versus the machine learning. Let's go ahead and run this pipeline. All right, now that the pipeline has successfully run, green checkboxes in all the nodes, let's open up the model comparison to compare the accuracy of the mixed model to the gradient boost. Our champion model is the mixed model that we used with a lower root average squared error. The average squared error would correspond to the residual of the holdout sample, and the root average squared error is the square root of that. And the lower root average square error, well, the lower the error of the test on the holdout sample, and the better the model accuracy. So in this case, our parameterized mixed model actually outperformed a machine learning model. And that's a nice state to be in when you have the right number of parameters and you have a rough idea of how to apply them in a mixed model. All right, so now we run our mixed model alongside a machine learning model in a multi-threaded environment to assess the accuracy of these two models and do it very quickly in a pipeline. Now, what's at the real cutting edge is that in machine learning pipelines, often you want to use expert knowledge about covariates, sites, blocks, units of replication that are not of interest to wash out the covariance before taking those predictors and running them in a machine learning pipeline. That's where random effects models are rising in popularity. See, E-bloops, or the estimates of random effects, have advantages in machine learning pipelines over estimates derived from fixed effects. There's the shrinkage effect, and it smooths out some of the error in the original measurement. Hence, you can pipeline mixed or random effects models along with machine learning pipelines to get better information from bigger and bigger data sets that we're seeing all over the place in all sorts of fields today. All right, now it's your turn to go and steal the thunder. But I'm on cloud 9 anyway. Hey, if you want to learn more, check out our mixed modeling course, or if you want to read about it, check out a book on SAS for mixed models. You certainly won't regret it. And don't forget, please subscribe to our channel, and we always look forward to hearing your comments and feedback in the comments. All right, everyone, it's been such a pleasure. Take care. See you later.